All right, so now we're going to look at the third concept for this part of the unit is the idea of the electric field. So the electric field is like a vector that goes around a charge or more than one charge, but that came down from the idea of the electric field came from the British physicist Michael Faraday, who really wasn't much of a mathematician compared to other physicists of the time, but he was very good at building experiments and figuring out how things work and coming up with good theoretical models of how electric charges and magnetic fields worked. But he was the idea of there has to be something that causes these to act at a distance, and these are some of the pictures of ways of visualizing electric field lines, similar to what you guys will be doing in the simulation lab. But the correlation to this is the idea of the gravitational field. Gravitational field is caused by the acceleration of acceleration of object caused by the Earth or by some other object. And the acceleration when it's close to the Earth is 9.8. And we looked at that in class, that 9.8 came from the universal gravitational constant, the mass of the Earth, and the radius of the Earth. And together that gave us that 9.8 value. Similarly, for an electric field, it's very, very closely defined. But basically, you imagine some charge Q is creating this electric field, not magnetism yet, and then you had some small charge Q0, and that electric field is generating a force on that Q divided by the test charge Q. So the idea is the bigger charge creates a force on the smaller charge by creating an electric field at that point. And so if you find the force and then divide by that charge, you can find what the electric field is. Much the same way as if you measure the weight of an object and then divide by the mass, you would get the gravitational field. So the electric field is just the effect of a charge at a distance, regardless as if there's anything there. You kind of felt that for those of you who were able to use the Van de Graaff generator. You'd feel the effect before anything sparked or even touched. We can usually ignore that later. But one of the ways we deal with electric fields is with the idea that you have a point charge, and that point charge creates this electric field. So if we know the force is just Q over r squared, and so if you divide by Q0, and then you end up with an effect almost identical to what we got with the gravitational field. So E is the gravitational field, whereas lowercase g was the E is the electrical field, lowercase g is the gravitational field. And the way we can visualize that is the idea that positive point charges create an electric field that points away from it, and then negative charges are where the electric fields end up. So if you have more than one, you get these loops. So you can kind of think of them as beginning at the positive charges and ending at the negative charges when you have a collection of charges. Because most objects are neutral, you don't get electric field lines created by them. But when you're solving problems using either force or electric field, make sure you start with the diagram. You figure out what point you're looking at or what particles you're looking at. Make sure everything's in SI, all the prefixes go away. Make sure millimeters convert to meters and nanocoulomb convert to coulomb, and you just have the powers of 10 to the minus whatever. Make sure you set up your equations, find any x components, find any y components, then use all of our vector identities to figure out what's going on. And one way that this was used experimentally is the idea that of the Millikan oil drop experiment. He was figuring out how to figure out what is the charge of an electron. And the way he did that was set up a place where you had a controlled voltage between two plates that basically allowed you to control the electric field. So the electric field in that area was related to how strong the voltage was. And they would fire in oil droplets, and as those oil droplets were falling, as they would go out of the diffuser, they would actually pick up an electric charge. And depending on what that electric charge was, he could try and make those float. He would look at those and kind of look at their mass and then be able to figure out what their figure out the known electric field, know what their weight was, and use that to find their charge. So it was the idea that all of the forces had to cancel out. So there's an upward force of Q times the electric field for the electric charge, but it also had mass, so it had weight, and so that was downwards, but if it was floating, those two had to be equal. So then he figured out, all right, so the charge has to be equal to mg over E. And he looked at that and graphed that and saw that it was only multiples of a similar charge. It was like a staircase instead of like a smooth curve, because each of those things were multiples of the elementary charge. And that's where that version came from. Now, Millikan actually made a mistake in his calculations and came up with the wrong value, but a lot of people repeated his experiment and got the same wrong value until somebody stood up and said, you know, that's actually incorrect. You should probably check your numbers because this is what we're getting. But that's where a lot of that comes from.